Off the coast of Italy, there are structures standing in the open ocean that have taken the direct hit of waves, storms, and salt water for over 2,000 years. Not steel, not modern reinforced concrete, just concrete, poured by Roman engineers who never touched a calculator, never ran a stress simulation, and had no idea what a rebar was. Meanwhile, a parking garage built in the 1970s, with all our modern engineering, is already crumbling.
For decades, scientists dismissed this as a mystery of lost knowledge. But in the last few years, researchers looking closer at Roman concrete found something that shouldn't have been there. Tiny white mineral deposits scattered through the material like flaws. For a century, engineers assumed these were mistakes, sloppy mixing by Roman workers who didn't sift their materials properly. They were wrong.
Here's what most people are taught. Roman concrete lasted because Romans used volcanic ash, a special ingredient called pozzolana, found near the town of Pozzuoli, mixed with lime and seawater. That's it. Ancient recipe, lost to time, end of story. It's a satisfying explanation. It's also incomplete. Because plenty of modern concrete uses volcanic ash too, under carefully controlled lab conditions. And it still doesn't perform anywhere close to what the Romans achieved with hand tools and no quality control standards at all. Something else was happening. And it took a team of geologists, material scientists, and engineers cross-referencing ancient Roman texts with electron microscope imaging to figure out what. The clue was sitting in plain sight for 2,000 years. Those white lime deposits everyone assumed were construction errors. When a team at MIT and Harvard finally analyzed the chemical composition of these deposits under high-resolution imaging in the early 2020s, they found something that didn't match sloppy mixing at all. The lime wasn't fully dissolved and evenly distributed, the way careless mixing would produce. It was clustered in specific reactive chunks. That's not a mistake. That's a design. So researchers followed the trail further. First, they discovered these lime clumps, called lime clasts, were made using a process called hot mixing, where quicklime is added directly to the mix at extremely high temperatures, rather than being pre-slaked into a paste the way modern methods teach. This produces exactly the kind of reactive, unevenly distributed deposits found in ancient samples. But that raised another question. Why would you want uneven, reactive lime sitting inside your concrete?
The second discovery answered it. When researchers deliberately cracked samples of this hot mixed concrete and exposed them to water, something remarkable happened. The lime clasts reacted with the water, dissolved and recrystallized, flowing into the crack and sealing it shut within weeks. The Romans hadn't built concrete that resisted damage. They built concrete that repaired itself. And the trail didn't stop there. Structures built along the Roman coastline, harbors, breakwaters, seawalls, showed a second, separate phenomenon. Their concrete, when exposed to seawater over centuries, didn't erode. It grew stronger. Rare minerals like aluminous tobermorite formed within the material as seawater percolated through it, reinforcing the concrete's internal structure from the inside, decade after decade. Modern concrete does the opposite. Seawater is one of its greatest enemies. After the breakthrough, there was never a lost secret ingredient. There was a lost process, hot mixing with reactive lime, that modern industry abandoned centuries ago. Not because it failed, but because it was inconvenient. Modern construction demands concrete that sets fast, meets uniform testing standards, and can be mass-produced on tight schedules. Hot-mixed, self-healing concrete sets slower and behaves less predictably in a lab. Exactly the qualities industrial building codes were designed to eliminate.
And there's a deeper irony sitting underneath all of this. Modern concrete's real weakness isn't the concrete at all. It's the steel rebar we add for extra strength. Roman concrete had no reinforcement, nothing to rust, expand, and crack the material from within. Modern rebar corrodes over decades, and as it corrodes, it expands, fracturing the concrete around it from the inside out. We didn't out-engineer the Romans. We traded their durability for our speed, and then added a hidden flaw of our own.
Today, that forgotten Roman process is being taken seriously again. Engineering teams are testing self-healing, hot-mixed concrete formulas for modern seawalls, bridges, and infrastructure meant to outlast the people who build them. The Colosseum wasn't built by people with knowledge we've lost forever. It was built by people who made a different trade-off than we did. One we're only now realizing might have been the smarter one.